All right, guys, we're gonna do some stuff on, they're called free body diagrams. You don't have to draw them to scale, but they should be proportional. And I'll show you how to do that. So you don't have to pull out a ruler. You'll see some stuff online where you could pull out a ruler and do it to scale, but there's, for what we need it for, we're just using these as a representation of forces to give us an idea on how to set up the equation. And then I will show you the proportional way as we go through these. There's going to be a lot of examples. There's 16 slides. I'm going to do all the odd ones. And so all the even ones are similar to the odd one before it, is what's about to happen. A couple rules. So that's free body diagrams. A couple rules. We're going to draw all forces acting at the center of mass. Even though like friction actually, if you got a block here, and we're pushing it this way, there's what we call an applied force, FA. Friction would actually be acting back along the surface. There's also this thing called, well, there's gravitational force down. That actually acts from the center of mass. The applied force, I guess technically, if you're pushing back here, you would say it's back here. And then the normal force is actually acting from the ground. Oh, that shouldn't have been that big. Here's where proportional comes in. There's nothing pushing it up and down except, well, gravity's pushing it down, so the table's going to pull it with an equal up. And we'll talk about all this, but I just want to be aware this looks like a mess. But normal force is actually acting here. Gravity is acting from the center. The applied force is acting back here, and friction is acting down here. For simplicity, because that's a mess, for simplicity, we'll draw it from the center of mass. And again, I'm going to complete the odd problems. You guys are going to do the even problems. All right, and here's our first example here. Oh, oh, sorry, it's moving the slide. Uh, so we got a falling ball. So you got to read these carefully. Falling ball experiences a resistance equal to half the acceleration due to gravity. The first force you're always going to draw on these is gravity. Gravity is always pulling everything down. And we're going to do that again from its center of mass, as close as you can get it. And then that's the gravitational force. We call it FG. Uh, the variables. So how we draw these and the variables is how I present them to you. If you come across something online or another description of stuff, that is fine to figure if you're struggling, but you need to figure out how we're doing it, how it correlates to what we're doing, because you got to show it to me my way. Fg is the gravitational force. Sometimes you'll see weight as a force, which it is, right? The gravitational force in this instance would be the weight of the ball, but we're going to avoid that notation and just use F for force and G for gravitational. Um, if so, but right, it didn't say it was free falling. It said experiences a resistance equal to half the acceleration due to gravity. Um, Equal to half the acceleration due to gravity. So this is going to have an upward force that's about half of this. And then this is where I was saying you don't have to pull out a ruler, but it should be smaller than the gravitational force. Experiences a resistance equal to half. And again, I'm reading it again just to make sure I'm reading that right. And then I would call this a frictional force. Here's one of those times where air resistance, you could call it force air. I'm going to treat it's as a friction, right? It's a frictional force, so we're just going to call it FF. We're going to try to be generic with these labelings. Now, that's the free body diagram. Write out the force equation. Well, the equation for these is always going to start the same. So if you just write sigma F equals ma, that's the generic equation. It's not going to get you anything though. Like that, it's the force chapter, so obviously that's the force equation. You have to be able to write out what is sigma F, what is M, and what is A. Now these ones aren't going to have any numbers. That we're going to save that for a little bit later. But so sigma is the sum of all the forces. Now we got to separate forces. Left and right forces are different from vertical forces. So you keep left and right together. Now this one doesn't have any left and right, so I don't have that problem. If there were left and right and up and down, we'd have two different equations. So keep that in mind. If you have forces going in different directions, you have two different equations. So this one just has vertical. So these are only acting in the y direction. So I just look at friction up, FF, minus FG down, equals, there's only one mass, so I keep M the same, times the acceleration. And then the problem's going to give me information to find those numbers. If again, watch the notation. Some you're gonna find some of this stuff online where they're doing different variations of this. It needs to be the way we're presenting it in class. That way I know you know what we're doing. When you guys come up with other methods, I'm okay with it, but you gotta have a one-on-one with me, and you gotta show me that you know why you're doing it. That there's a reason for it. If there's not a real reason for it, I'm gonna even if you have a real reason, I'm probably going to still force you this way. But this is just clearly showing me that you know there's a force up, friction, force down, gravitational equals mass times acceleration. And then I know you're good. I know you know what you're doing. So the next one, so that's that. And then, like I said, the even one's going to be something similar, a little different description, same idea though. Slide 3. Sorry, guys, I'm going to try to make this quick, but uh, quicker because this is going to take a minute. So, person accelerating on an elevator. So we go to the person's center of mass. Gravitational force is pulling them down. Uh, and it says they're accelerating. Person accelerating on an elevator. Now the image is showing an upwards acceleration. So typically, if there's not enough wording in the setup, then we got to look at the picture. So this one says person accelerating on an elevator. And then this is showing us that it's upward. So to be accelerating, the force from the elevator has to be bigger than gravity, or you would not be accelerating upwards. And that we call, anytime you have a surface force, anytime you're touching a surface, we call that a normal force. And then that's Fn. So again, if we're going to do the equation, sigma F equals ma, what are the two forces? Well, these are also vertical, right? So there is no x again. There's no left and right. It's just Fn minus Fg. Again, there's only one mass, so we just do m times a. If there were multiple masses, we'd add up the masses. But and then that's the equation. They got to give us that information to find. That's an awful G, sorry, to find this stuff. And then look at it. It basically looks like the same one, except the force that's causing the acceleration is different. Instead of air resistance, it's instead of air resistance and gravitational, it's normal force and gravitational. This one, be careful with this one. I meant to fix that up. I'll try to fix the picture before you see this. It says constant oh no, it's fine. Constant velocity, 0. Okay, we're okay. Never mind. I thought something was wrong with that one. Draw an elevator cable. Oh, I know what's wrong with that last one. Sorry. That it says person on an elevator at a constant velocity, and then in here it says that it's not moving. Let's just say it's, I don't know, 10 meters per second. The velocity doesn't matter, just that it's constant when you get to that one. Sorry, but if I remember, I'll try to swap that picture out for the right picture. Tension on an elevator cable. So now we're looking at the cable uh, pulling on the elevator. So I'm gonna say my points. I don't know where we want to put the center. Uh, oh, yeah, let's just put it here. The tension on the elevator. So gravity again is always pushing it down. Tension on an elevator at a constant velocity. So to have a constant velocity, the forces have to be equal. If the forces aren't equal, then you have an acceleration. So this one would have a tension force up that's about the same, well, that is the same size, not about, is the same size. So again, we got sigma F, sorry guys, getting sloppy as I get faster. Sigma F equals ma, and then again, T is up, that's the tension force, minus Fg, which equals ma, oh, no, sorry, ma. Um, and again, then they would give us numbers. But again, look at this. It's vertical. These are only vertical forces. We haven't seen any horizontal yet. We'll get there. Uh, the but it looks identical to the other equation. A force up minus a force down equals ma. It's just a different force now. Now it's a tension force, and we're going to use a capital T for tension. Then you're going to do a similar one on 6, 7. Here we finally get to a horizontal. Now it still has vertical forces, but the acceleration's acting horizontally. So we're gonna have a bunch of forces, maybe a bunch of forces. We're gonna have forces horizontally, which equal max, and we're gonna have forces vertically, which equals may. I hadn't been subscripting the y's. I've just been anyway. The force is vertical, the acceleration is vertical. They go hand in hand. You can't have an acceleration without a force. in the direction you're accelerating. The car accelerates on a rough horizontal road. So let's start with our normal. Gravity is definitely pushing this down. Normal force, the road is pushing it up, and then you're gonna get Fn minus Fg equals ma. Now, it's not accelerating up and down, so this would equal 0. And when we go to start putting in numbers, there are going to be times when you know it equals 0. And then so Fn would equal Fg. That's all that statement's saying. So that doesn't help us with the acceleration of the car. So then we're going to look at the horizontal forces. Well, it accelerates on a horizontal rough road. So there's got to be some applied force forward. And then that's from the, well, here, how you want to be specific. It's the tires pushing on the road due to the motor. So again, we're just drawing it from the center of the car. But that's what we call FA, an applied force. Now there's friction. It says it accelerates. It doesn't say if it's accelerating to speed up, slow down, but it cannot be the same size. If it's the same size, if friction is the same size because it's a rough road, then you're telling me it's constant. So it either has to be bigger or smaller. I would, for a normal car, typically the frictional force is going to be smaller than the applied force. So it's going to hinder your acceleration, but not stop you. But this one's vague, so it could be bigger. It just cannot be the same size. So for this one, how many forces do we have left and right? We also have 2 forces left and right. I'll say on average, it's probably 2. Could be up to 3, or 1 for that matter. FA minus FF equals MA. And then we know, well, I'm sorry, then they'd have to give us information about the applied force minus the frictional force. But again, look at these equations. They all look the same. So if they're opposing forces, you subtract them. All right. And then what friction is and how to get that information, that we are going to do a little later here. All right, cars. Oh, that's you guys. This one is oh, keep moving the picture instead of the slide. Dynamics cart is accelerated across a smooth table. So this thing's acceleration is happening like this. The accelerations don't actually go in the free body diagrams, but you can draw them off to the side. Just don't connect them to anything because they're free body diagrams are forces only. I'm just making an indicator so we know which way we're going here. So I got a lot going on here. I got this cart getting pulled down by gravity. I got the table pushing up on it with a normal force. It's a smooth table, so there is no friction. I got this mass over here, which is pulling down by gravity, and then it's the string, the tension in the string is tugging up on it. And then that tension is going back along here, and because it's accelerating, should have made that T a little smaller. Shoot. Sorry, guys. So we're going to make that T a little smaller. So you also have a tension off of this guy that would be the same. These T's are the same because it's the same string. It's just being redistributed. So this one's got a lot going on. We got 2 different objects. So this one, again, it's all sigma F equals ma, but for different objects. We got, and then this one has 2 forces. What I'm going to tell you right now, though, is this Fn and this Fg, they're equal to each other. So we could write that out. Well, let's do it. Fn minus Fg equals ma. But they're not accelerating up and down, so this just goes to 0, and it tells you that Fn equals Fg. Now this Fg is for the cart, and this is for the block. So we're going to have a C on this one, which is the acceleration of the cart. Now we got a T forward, so if we do the other equation, this is horizontal, we just have T acting on the cart equals MAC, the acceleration of the cart. So there's 2 equations. We're going to do the same thing with this one. This one has no left and right, so all we're going to get on this one is T minus, but it's always sigma F equals ma. It's the same silly thing every single time. Now this is the mass of block 1. This is the mass of block 2. Sorry, I should have been labeling that. And then now we're going to have the acceleration of the block. I didn't realize they numbered them. We could have been doing, instead of cart and block, we could be doing 1 and 2. Just so you can decipher between the 2. Now this is a mess. So I could get the acceleration of the cart if I had the tension. I don't have, well, we don't know what we have because they're not giving us numbers, but that would be one viable way. The other thing over here is it's not going to give me, well, now this one's going to give me the acceleration of the block. Now they are attached, so should they have the same acceleration? Yes, right? They're attached. and I'm going to show you one more equation. This is already a mess, but what I'm telling you, there's multiple ways to do these. You would just pick one and go with it and see what you have. The last one I'm going to write, though, is the one that would actually solve this outright, depending on what they gave you. Like that's the trick with, we're just drawing the forces, so we don't absolutely know what we have, number-wise, what we have. We know what forces we have. But this one, you could get the acceleration of the cart if you knew the weight of this block and the mass of block two and the tension in the rope. You could get the acceleration of the block, and then the acceleration of the block would be the same as the acceleration of the cart. Blah blah blah. Here's the other option. You treat it as what we call a system, and so this that I'm drawing here is the system. Right? I circled the cart and the mass. Any forces coming out of my system are going to cause us to accelerate. Any forces inside this circle are not going to cause us to accelerate. So what happens is those T's are what we call internal forces, and they don't affect the acceleration. So we can, if let's just say we don't know the tension, we can still find the acceleration of this system because it's going to be still sigma F equals ma, but what's the only force causing this to accelerate? There are two forces, this Fn and Fg, the gravitational force of the cart, are coming out of the system, but they're canceling each other out, right? It's not accelerating up and down, it's accelerating horizontally across the table. So the only force coming out of this is Fg. It's the weight of the block equals. Now, how many masses are in my system? I circled 2. So it's m1. I lost the ability to write again, guys. M1 M2, oh, plus. Sorry, trying to do this with my finger. Plus M1 plus M2 times the acceleration. It's the same acceleration, so you don't have to really specify if it's cart or block. They have the same acceleration. But that is how you would get the acceleration if you don't want the tension. Now, if they ask for the tension, then you got to go back and find, then you could find the tension, but the tension's the same in both cables. It's the same cable. So you find it. You could use this the equation you wrote over here to get tension, or you could use this equation to get tension. The problems with numbers will be more specific and narrow it down on what you have to draw and what you don't have to draw. All right, let me go to the next one here. 10, you're gonna do 11. The free body diagrams on an incline get a little trickier. And I'm gonna pause it here for a second to get my pen working again. All right, guys. Hopefully my pen keeps strong enough. For the incline ones, still always start with gravitational force straight down. These ones take a minute, and you'll probably get them kicked back to you to fix. So go slow with these. When you're on an incline, your what you consider on a flat surface, this would be x and this would be y. But on an incline, this is going to be x. Sorry, guys, this is going to trying to freehand this. That's going to be y. It's your xy axes, but picture yourself on a hill. It's going to be tilted. So the forces aren't lined up with an x and y. Uh, so if when so if we're doing problems with these, you'll have to do some trig stuff, and that'll just be if we have time, we're going to come back and do the angled ones. So we'll draw them, but we might not calculate them anytime soon. So you still got gravitational force down. Now the normal force is perpendicular to the surface, so it would be that way. Now how big do you know to make it? This is where the parallelogram method comes in. Um, Actually, in this case, it's going to make a triangle. I can come down here. There's part of the gravitational, well, we should not label this though. It's not part of the free body diagram. I'm just showing you what happens. Part of the force is acting down, and so I'm dotting it because they're not really there. But there's your triangle if we were to get into sine and cosine. But we'll come back to that if we need to, if we have time to come back to that. But what I'm telling you is this part of the this dotted, this vertical part of the triangle is equal to Fn. They would be equal and opposite. Um, but we would not label those because they're not the actual force. The actual force is the gravitational force, which I drew straight down. A car rolls down a smooth hill. So what's happening here? I am going to label y and x though. that part of the force is going into the y directions, part of the force is going in the x direction. So this car rolls down a smooth hill. It doesn't say if it's constant speed, doesn't say if it's accelerate. Well, doesn't say if it's accelerating or constant speed. So this is it. This is the free body diagram. If it is set this for acceleration. So how this works, this one's going to be weird because FG, so it's sum of all the forces, but FG and FN don't line up. So before, when we were doing FN minus FG equals MA, that was okay because they lined up. This time they don't line up. So we got two directions. The gravitational force is actually acting into the incline and down the incline. So we got to account for that. So if we're doing the y equations, it would be Fn minus Fg, but the y part of the Fg. The angle would be right here. This angle, the angle of the incline and the angle in this side, this triangle, would be the same. It's a trig thing, geometry, where I guess it's more geometry, but where two triangles share the same side, they have the same angle, blah, blah. I don't remember what it's called, but it's the angle's the same. Equals mass and acceleration in the y direction. It's not accelerating in the y direction, so the normal force would equal FGY. And most likely we know the mass or the weight of the object, and we could solve that. Horizontally, though, car rolls down a smooth hill. That's what it wants to know. So we got our other equation in the x direction. Right, these are all x's. How many forces are acting in the x direction? Well, it looks like none, but remember FG is tilted because it's on an incline. So part of FG, specifically the x part, is accelerating it down the hill. So we get FGX equals MAX. Now, if there was friction, we would subtract out friction. So you're still subtracting out friction. So nothing new with that. All right, and then you're gonna do 12, 13. We got another one. Car rolls down a rough hill. So here's a friction example. So rough rolls down a rough hill at a constant speed. So we got friction this time. So you're gonna draw FG straight down. You're gonna do, I would maybe just dot this so you know it's not actually, this is just your axes to line things up. And then because that, well, here, no, let's keep drawing the forces. We got Fn up. Fn's gonna equal this the y part of the force down, and then here you got the x part of the force. Don't, I'm just putting x and y to tell you that one's vertical, one's horizontal. Um, do not label them FGY, FGX in the free body diagram and dot them. Dotted lines aren't really there. There's only two forces. Actually, there's a three because it's a rough hill. You're going to have friction going this way. Now, how big do I make friction? Well, it has to, for constant speed, it'd have to be equal to the force down. Well, the x is the force down, so friction is only going to be that big. Um, if it was accelerating with friction, then you could make it bigger or smaller depending on if you're speeding up or slowing down. But that's the three forces, Fn, Ff, and Fg. Now, how you write the equations, again, we got, whoops, multiple, we got Fgx equals Max. We got Fg, every time, guys, I don't know why I keep trying Fg. Fy equals MAY. My brain's a couple steps ahead. How many forces are acting horizontally? There are two. Force of friction minus FGX equals MAX. I know this looks foreign to you. It's going to take some time to get used to these ones, especially the inclines. But force of friction is up, minus FGX, which is down the incline. Not straight down, but down the incline. Because the accelerations, well, not the acceleration, but the velocity, the constant velocity is that way, equals MAX. For the vertical, you're going to end up with Fn minus Fgy equals MAY, and it's not accelerating vertically, so the AY would be 0, and then it's just telling you that Fn and Fgy are the same size. All right. So again, this will take some practice. You might want to message me or sit down. We can do a one-on-one, that kind of thing, or just watch this again if you need to. But takes some time. 14, you're gonna do. All right, last one, guys. Sorry, this was long. I tried to get every scenario. I mean, it's not every scenario, but the big ones that you're gonna come across. This is called an Atwood machine. For the lab, you did what we called a modified Atwood machine or a half Atwood, where one of the blocks was on a horizontal surface. We're going to say friction is negligible. It's a pulley system, so it's a rope draped around this pulley, like an elevator. One goes up, one goes down. Block one is accelerating downwards. So off to the side, I would just make a note that, hey, the block one is heavier, right? It's more massive and it's following downward. So for this, let me get this more centered so you can see everything. All right, so we got this is similar. Well, we already did the modified outward. I guess I might not have called it that though. With the cart on the table, that was a modified outward. So from the center of this object, we got a tension force up and we got gravitational force down. Now it is accelerating this way, so this gravitational force should be your bigger vector. Sometimes if it's not, as long as you're not making it dramatically different in size, I'm not going to be that picky about it. But um, like those almost look the same size. But as long as I can tell that it's not some huge tension force, then we're good. Uh, so on this side, uh, we're also going to have a graph. Now this is a FG1. Now because it's accelerating towards FG1, FG1 is bigger than FG2. So FG2, the T is going to be the same size because it's the same rope. The tensions are going to be equal, same rope. FG2 should just be a little less. But here's what I'm saying. They all basically look the same. As long as it's not dramatically different, like that's what I'm looking for. Like that you haven't that they're not overly just random sizes. And again, once we get into numbers, like you're just sketching these real quick, like it's not gonna super matter. But when it pops up on, like sometimes they'll give you multiple choice questions where it's like, what is the correct free body diagram? And they'll have them in different proportions. That's when you'll need to know it. So here's our two objects. So we're gonna have two equations again. There is no horizontal, so we're gonna have uh, where can I squeeze? Well, here I'm gonna do it up here. So this is that's awful. So this is FG1 not FG guys. It's the sum of the one forces equals M1A. And then over here, we're going to have the sum of the second block equals M2A. So then ask yourself, how many forces? This is like the first couple ones we did, right? T minus FG1. We just have to be a little more specific because we've got multiple objects going on. And then T minus FG2 equals M2A. The acceleration, the tensions are the same. It's the same cable. The accelerations are the same because they're attached. So that is one way to solve. There's two equations, two unknowns. You could do, I don't know how many of you enjoy these simultaneous equations. I find the math interesting, but I don't know that everybody does. But that is one way. You could do a substitution in here. We could solve this one of these equations for t and substitute it into the other, or solve for a and substitute it into the other. The other option, the way I would recommend, is treating this, like I said, like a system. So this, follow the rope, circle the center of masses, come back up. There's our system. Everything inside that blue line would be internal and doesn't matter. It's an internal force, so we don't need to worry about those. The forces coming out of it, those two FGs, will cause it to accelerate. So we can do another sigma F, but this time we're going to look at both blocks. And then this way we don't need the tension of the strings, which typically they don't give you. Yeah, usually you are doing it this way where we don't know the tensions. So this one, because FG1 is bigger, well, how do we, well, here, let's do it this way. Because FG1 is going down, that would be my negative. FG2 is going up. So I'm going to start with FG2 because it's positive, because it's going up, right? This is FG, well, here it's not F, the FG2 is down, but the block 2 is going up. It's accelerating upward. Block 1 is accelerating downward. So FG2 would be positive because it's an up, since we're defining down as a negative. And then that's just our norm. Like, it's not like you have to define down as negative, but for us, for simplicity, we're going to keep down as negative. So FG2 minus FG1 um, equals, those are your two forces. Those are only two forces coming out of my system, my circle there. Well, circle, the whatever you want to call that shape. Now, how many masses are there? Two. M1 plus M2 times A. They have the same acceleration. So if we have if we have the two masses, we can solve for the acceleration of the system. I know you're excited. You're gonna have to wait a little bit before we start putting in numbers. You might not be able to sleep. I understand that. And then sorry for the length of this video, and I am done.